Okay, we're almost there. Mystery powders and develop the atomic theory. The first half of class, we were able to complete the mystery powders lab, and I'll let you know how you can complete that when you come back. The next lesson was on developing the atomic theory. Um, the first part was an exercise. I got everyone to cut out these pieces. So every single person got one of these, as well as one of these. Okay. I wanted at the class to see if they can organize these pictures from least complex to most complex to show the evolution of the model of an atom from way, way back, like 200 years ago, all the way to now. And then see if they can match the model, the physical model, with the scientist that was responsible for it, simply based on the description I gave them. I didn't spend too much time on it. It was about, 10 minutes or so. And the order in which you can try it yourself, but the order in which we placed them on our sheet was included was 1, then 2, then 3, then 4, then 5. So this planetary orbital model is the last and most modern one up to the grade 9, ninth grade. When you get to grade 11, things start to fall apart and we need to learn another model. But for now, just wait until you get older. To match this, let's see if I can do this even though it's scrambled on the fly. The very first person that we need to name is John Dalton. Okay, he had the idea that everything was not made of, earth, wind, fire, and yeah, whatever. Okay, earth, wind, fire, and water, not the elements from whatever BC. He hypothesized that every single molecule or every single matter, every single substance out there was made of atoms. Atoms are small particles. And so we called this just a billiard model, right? Their cement is cement particles. Again, water is water particles. Mouse is mouse particles. I don't know. It's called a billiard model because every single particle would be different, but they are round and they are small. From there, we have J.J. Thomson. Okay, Thomson is number 2. And so instead of just billiard balls like that, every single atom has negative piece. Let's see. Has plum pudding model. Positive and negative. Yeah, negative pieces stuck around a large body of positive. Sort of like a cookie. Hence the name chocolate chip cookie model or the plum pudding model, depending on where you're from, the name can change. Anyway, sort of like a raisin bun, okay? From there, we had Rutherford saying it's not actually a whole large body of positive, right? Yes, there's negative all around, right? But it's not the entire atom that's positive. The positive is actually concentrated in a tiny little thing in the middle. Hence, we call it the nucleus. And that nucleus has to be positively charged. He accomplished that with a gold foil experiment. Long story short, he was taking atoms and he was going to punch it with other particles. And what he expected was these particles being so strong, it was going to just rip through the atom and it would have no problems punching through these atoms. However, a lot of them did go through, but there were some that actually was bounced back or bent and deflected out, which makes no sense because literally that is the analogy of a cannonball bouncing off of tissue paper. Like, how does that make any sense? So there must have been something else that's pushing it besides just its density. And so they discovered that there must be a very, very concentrated positive thing in a tiny piece of the atom, which allows most of it to pass through. But occasionally, when this huge cannonball hits a direct makes a direct hit with the nucleus, it has no choice but to bounce back. Then comes Chadwick, and I don't really talk too much about that. And again, we go more into the details of the scientists in grade 11. And so I don't want to talk too much about that in grade 9. I want to focus on the actual model itself. We got Chadwick, and then there's Bohr. Okay, electrons are found around nucleus in shells. Oof. Okay, so moving on. Now that we've established, what the general, I guess, flow of the, come on, can I get this out of the way, please? Yeah, flow of the, I guess, the evolution of the atoms. We can talk about this final model that we've come to. If you want to hit summary, I highly recommend you watch this video. And just for fun, to have a better understanding of what this shape actually looks like in real life, I recommend you watch this just for fun. Once you've done so, we can talk about the three main parts of an atom, namely the three building blocks of an atom, which are electrons, protons, and neutrons. Electrons are the things that are found on the outside. So outside nucleus or orbiting around nucleus. Protons are found inside nucleus, and neutrons are found inside nucleus. Protons, as a name might suggest, are positive. Neutrons, as a name might suggest, are neutral. So it has a charge of +1, has a charge of 0, and something then has to balance the proton's positivity, and that would be the electron, sort of keeps it in check. So these are like, why am I writing electric? Negative. Okay, next. Electrons are essentially massless. They're virtually 0. Okay, and protons and neutrons, they both weigh something. But what does it weigh? Can I use the unit grams? No, it's way too big. Can I call an atom 1 milligram? No, that's still too big. In fact, there is no metric unit that can actually weigh how much a proton or neutron is, at least right now, in the grade 9 level. So we call this 1. 1 what? Well, we needed to give it a unit. So we called it an atomic mass unit. It's literally just 1. So we call that AMU. Neutrons too. It's slightly heavier than our proton, but it's close enough that we're just going to call it 1. Okay, let's move on. An atom is the smallest particle of an element that has the same properties of the element. Each element consists of a unique atom with a different combination of the 3 subatomic particles. In other words, every atom, every different kind of atom is different because it has a different combo of these 3. And I'll get more into detail later. There are 118 different types of elements that we know of that make up matter. Therefore, there are 118 different atoms, different elements, okay? All right, this part is where it gets a little mathy. Because we just talked about its charge, protons and electrons balance each other in terms of charge. Protons and neutrons are heavy or heavier. If you take a look at these elements in the periodic table, they are all given a specific number. So if this was like a basketball team, you can think of each of them having a unique jersey number. But where do these numbers come from? Are they arbitrary? Did tin just feel like, is tin the 50th element that they discovered, so they gave it the number 50? The answer is no. Germanium, in this case, has an atomic number of 32 because it was discovered to have 32 protons. Lead is 82 because it has 82 protons. In fact, the atomic number is given so because it has that exact number of protons in the nucleus. Does that make sense? Next, if the protons are positive, Remember how earlier we said that we need to balance that positivity? The electrons are therefore negative, and if they balance out, 32 protons must be balanced by 32 electrons, 82 protons must be balanced by 82 electrons. So these are going to be equal to each other for a neutral atom, which leads us to neutrons. How do we calculate neutrons? Well, the mass comes in handy. Remember that we said the mass of electrons is virtually zero. But if the atomic number is 32, so the proton is 32, but its total mass is 73, where did the remaining 41 come from? It came from the neutrons. So take a look. If the atomic mass is 73, that is because the number of protons plus the neutrons is 73. Same thing here. If the atomic number is 82, but it weighs 207, well, what adds with 82 to get 207? 125. Remember, electrons is virtually zero mass. Oh, 1 second. Okay, and that's about it. Just as another example, I'll just randomly choose something. Here's nickel. Nickel, it has an atomic number of 28, which means automatically has 28 protons. Well, for a neutral atom, if it has 28 protons, it's got to have the same number of electrons, which leaves us for the number of neutrons. If the total mass is 59, that means in the nucleus, 28 protons must be paired up or must be sort of matched with 31 neutrons. That's it. Okay. Try the rest. And the answer key, I believe I already put up on our classroom on the wall. Color, luster, and state, that is there because I actually had a small sample of each one. And you can actually take a look at what that looks like. And yeah, just quickly report very quickly what they see and blah, 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 blah. Okay, that's it. We'll move on to you know what? Let's make this video for subatomic particles very quick. Oh, never mind. We didn't get to subatomic particles and the Bohr-Rutherford diagram assignment because of all the interruptions. We sort of ran out of time, and our mystery powders was also done in a different order. So after this video, I think you're basically caught up. I look forward to seeing you next week, and yeah, good work.